Good afternoon. Make sure you're in the right room. This is the Amazon Redshift Deep Dive. My name is Eric Ferreira. I'm a database engineer with the Redshift development team. And sharing the stage with me, I have Ari Miller, one of our customers. We're going to talk about specifically today tuning and best practices for performance on Redshift. Here's some of the topics we're going to talk about today. Ingestion, some recent features we added for you, some migration tips, workload tuning, and then I'll have the privilege to have Ari from TripAdvisor talk to you about how they implemented their Redshift environment for performance. And I highly recommend you stay to the end. In the beginning, I took a picture. I will know who left or who didn't. Okay, so be aware. So this is an advanced session. I'm not going to go to the details of Redshift, but it's always good to remember Redshift is our fast, simple petabyte scale data warehouse for less than $1,000 per terabyte per year. And today, I want to focus on the fast part. And there are many customers that are really happy about the performance they get with Redshift. And the idea of this session is to make sure you also that are using Redshift can achieve the same performance as those customers are enjoying. Here's a review of the architecture of Redshift. We are a columnar, multi-node, share-nothing cluster database service. And you have a leader node where you connect for SQL, and then the compute nodes where the data resides and all the work happens. And a lot of the operations happens in parallel directly through the compute nodes. And that's some of the things we're going to talk about today. If you focused on the compute nodes details, you're going to see that the node has different slices. And the unit of work on Redshift is actually the slice. And so it cares more about how many slices total you have in your cluster than the number of nodes you have in your cluster. We have two platforms, one with SSDs that has different types. They have the large and 8XL. And normally we have ratio 1-to-1 slices per CPU. And we have our dense storage nodes, which we have hard drives. And on this particular platform, we have 2 CPUs per slice. And by the way, these are DS2s. If you're still using HS1s or DS1s, I highly recommend you move because it's double the CPU, double the memory, same price. No brainer. So focus on how Redshift does the work on each slice. We're going to talk about different things to achieve the parallelism, the performance you need for your workload. So first, let's talk about ingestion. If you copy a single file into Redshift, only one slice is doing work because the slice is the one that copies a different file. Each slice copies a different file. So instead of getting 100 megabytes per second, you're going to get 6 megabytes per second, and that's not fun. If you have enough files, then on the phase 1 of your copy command, you're going to have every slice doing work, and then you can achieve the 100 megabytes per second per node and expect to scale near linearly as you add more nodes, assume you have enough files to feed those slices, right? You want those files to be similar size amongst each other, of course, and just one extra tip, files between 1 megabyte and 1 gigabyte gzipped works best in terms of performance. Another thing related to ingestion is the primary keys. Redshift allows you to add primary key to the table and to define them, and it's good documentation for you, and the optimizer can use that information to make optimizations during the query. However, if you try to load the same data twice, Redshift is not going to complain. We don't enforce primary keys. But we still recommend you to use them. So make sure if you declare a column as primary key, you maintain that unique. Otherwise, you might get wrong results when the optimizer assumes the data is unique, and it's not. Also, when you're loading data into Redshift, you might create a number of files on S3 and immediately try to copy with a prefix. Given the eventual consistency on S3, you may not see all the files immediately on the other copy command, so you might leave some files behind. And of course, you can go on STL load commits and see which files you actually loaded and make sure you got all the files you wanted. But if you use a manifest file, then you declare what exact files you want to load, and what you do if the file is not there, error out or ignore, and at the end, you guarantee you load exactly the files you wanted to load. The beauty of the manifest file is that if a file is supposed to be there and it's not, it retries a few times, so the file might show up. And if it doesn't show up after a few tries, that is when it errors out. Let's talk about data hygiene. Lots of customers create their cluster, start loading their data, are amazed by the performance, and a month down the road they say, oh my God, my performance tanked. Something's wrong. And they're not doing data hygiene. So gathering stats on table is very important for the optimizer to know which table is bigger, which table is going to return more rows, so you can do the joins on the right order. So every time you add rows to a table, you should analyze at least the sort key column. It's very fast because you do on a single column, and it's enough for the optimizer to know the size of the table. Weekly, you should do a full analysis of all the columns so the optimizer has better statistics about all the data in your table. There is a view we added recently that's called SVV table info, and the column called stats off can tell you how much % of the table has stale stats. And then you know when to gather stats. Also, you can look on the STL alert event log for tables that are missing stats altogether, if you never gather stats on a table, which is possible and can cause you a lot of problems. Vacuum. Vacuum, I don't want you to run with every load. Not part of your ETL. Vacuum is a very expensive process. You want to run kind of once a week is a good start and see how that works for you. Use for your environment the number of unsorted blocks as a trigger to know when to run vacuum on your table. Again, if you look on SVV table info on the column unsorted or empty, you know when it's time to run vacuum because you deleted too many rows or because you have too many unsorted rows. Be aware, however, that if you have too many unsorted blocks or too many deleted rows, it might be faster to do a DP copy of your table, create a brand new table, just copy the data over, then run vacuum. Usually that threshold is about 20%, but your mileage will vary. Automatic compression. It's a great thing because automatically compress the data for you. You get better performance on your scans and lower costs on your storage because you can fit more data in less space. And what it does is actually samples the data, about 100,000 million rows worth of data. It tries to compress every possible way, figures out which one is going to be smaller, drops the table, creates the table again, and starts loading all over again. That's great to do once, not every time you load the same type of data. So if you load using copy command into an empty table, like a staging table or a temporary table, load the data, analyze compression, define what's the best compression for that column, for each column on that table, and then you bake those on the create table. Then you don't do auto compression every single load. It can cost you a lot of time loading if you try to figure out the compression every single time. Okay? Talking about compression, be careful when you compress your sort keys. On Redshift, we use zone maps to figure out which blocks we're going to actually scan. Now, we start on the sort key because your workload is likely to be on the sort key. And if, for example, you have a column 1 there to be your sort key, it's highly compressed. I have 100,000 rows on a single block. When I find the one row I'm looking for, it marks that block. OK, I need to scan the row offset of this block. So I'm going to scan between rows 0 and 100,000. When I go to the other columns, like in our example, column number 2, which is 5 times bigger, I'm going to scan 5 blocks for each one block of the sort key I need to scan. And that can be wasteful if my data is only one block of every single column. The goal is to have all columns similar size between the sort key and the non-sort key column so I can most efficient map row offsets from one column to the next. A good rule of thumb is don't compress the sort keys. Compress everything else. Don't compress the sort keys because usually the sort key will be a date or an integer or something like that. And you compress really well because of you ordering by that. So be careful. Rule of thumb, don't compress sort keys. Now, if you want to check your data for possible problems, again, SVV table info, there's a column called SKU sort key 1, which is the ratio between the largest column after compression and the first column, the sort key. If that number is too big, you might have this problem. And if you have this problem, even having the proper sort key and even having the queries using the sort key, you're going to show the alert that says very selective filter, meaning it scans too many rows or too many blocks in our case to return too few rows. And that's their sign that either your sort key is wrong or you need to uncompress your sort keys. As you create or design your tables, you want to keep your tables as narrow as possible in terms of the size of your varchars. We only store the amount of data that the varchar has. However, as we pull the data back, we create a buffer of the declared size because we don't know how much the size of the data we're going to get back. And wider means less rows in the same memory means spilling more to disk and low and poor performance on queries. So make sure you don't have a varchar 2000 for a state column of 2. Okay? I've seen that. Trust me, I'm not kidding. Look at your tables on SVV table info for the max varchar. And that might give a hint that you have a varchar 64,000 that maybe need to exist. If you have the data that fills a large varchar, that's fine, right? But if you don't create a bunch of varchar 1000s, varchar 256, when you need 2, 10, 12, right? Be careful about how you size your table. Now, I want to talk to you about some recent features we launched. And some people, I have a customer talking today where he said, you know, I got surprised you guys launched such and such feature I'm going to talk about here, and we didn't know for a month. So there are lists on the AWS blog that you can see what's new and get the new information, but who has time to be looking for what's going on all the time? So I want to catch you up on the new features that can help you with performance as well on Redshift. We added a number of new SQL functions. My favorite is list egg, and there's 2 versions of it. There's the window function version and the regular aggregate function version. We added approximate count, drop if it exists, and a number of others. And we keep iterating, and we're going to keep adding more functions for your workload. But we also want to allow you to create your own functions. And we launched user-defined functions. You can write your code in Python 2.7 and use whatever you want in terms of how you're going to use your functions. We still want to hear about specific functions you use a lot that might be useful for other customers. We might bake that into the system directly. So don't stop talking to us about what features and what functions you want added to Redshift. We still want to listen because we might add them for you. The library we added for Python already comes with pandas, NumPy, and SciPy. And you can create and install your own libraries. And it's a great, great use case for example, you create outside the database a huge scoring model, very complicated, save on a small little Python library, load the library on Redshift, and use to score very fast your data. So there's limitless applications, and we love to hear what you're going to do with UDFs. A couple of examples could be like if you have a host name to extract from a URL, you could use a regex, but it's kind of complex. You might miss the comma here and get something wrong. Or you can create a UDF that makes it simple for anybody to pull a host name out of a URL. That's a simple example. That's a kind of child's play. We had partners that as soon as we announced the feature, they created a list of examples of UDFs that are quite useful. Both Looker and Periscope created a very good set of functions, some related to date manipulation, JSON manipulation. I highly recommend you take a look. Go, they have tons of them. And we love because it immediately can be useful to you on your application. Talking about partners, Don't forget, there's a number of partners that have their services run directly on top of Redshift that you can deploy together with a single click. Things like Attunity or MicroStrategy or Looker. So make sure you don't forget that the marketplace can have things for you. Now, I want to talk to you about interleaved sort keys. We added some time ago, and we're making it better as we process and get more feedbacks from customers. And we want to make sure that you understand what it does and how it can help you with your queries. So before I go there, let me explain how compound sort keys work. When I have a table with a compound sort key, I sort everything for the first column, in our example here, customer ID. And then for the same value of customer ID, I sort everything by product ID. The table is physically ordered by that. Every column, even though it's a separate file, it's ordered by the same order, sorting by customer ID and product ID. So my first SQL you see there, when I do a query, and let's say customer ID equals 1, for example, I will hit only one block. Because of zone maps and min-max values, I know I don't have to scan all the blocks. Beautiful. I get the sum, I only open that file that has the amount, and my query is really, really fast. When I want to sum by product. Now, I'm using the second column of the sort key, and it doesn't help me. I have to scan the whole table. And because of parallelism and brute force share nothing cluster, it's not that slow, but I have to scan the whole table. It's linear cost. I have to scan the whole table. The interleaved sort key, instead of sorting by one column, then by another, what we do is we get all the columns you declare on your sort key, and we get bits information from all of them in a complex math equation, and we order the table by that result of that math equation. In our example, now my customer ID is spread across 2 blocks, and my product ID is scared about 2 blocks. I have like a 2-dimension way of entry on the table. So I mixed up product ID information and customer ID information on a new value, looking at my distribution of data to find the best mathematical function that will represent the new number and order by that. When I query by product ID, I hit 2 blocks, not 4. When I query by customer ID, I hit 2 blocks, not 1 anymore. However, if I hit by customer ID and product ID, I go straight to a single block. So it's a great feature if you have tables where sometimes you query by product, sometimes you query by customer, sometimes you query by region, and so forth. It can be very helpful. Many other databases, what they do is makes you create another index or a projection or a join index, however they call it, but it's redundant data. On this case, there's no redundant data. The data is ordered in a different way, and mathematics makes us scan in a log-n fashion instead of linear on the table. The way to use the feature, you just add the interleaved keyword on when you create the table. You can have up to 8 columns on the interleaved sort key. And of course, the more columns you add, the less each one gets relevance on the scheme of things. And the data, as you first copy into the table, we analyze the data to create that special function. Over time, if the distribution of your customer IDs and product IDs change too much, you get skew on the function. And we have a way to monitor that. So if you look on the SVV interleaved columns view, on the interleaved skew, when that number grows, like above 5, it's time to run a command called vacuum reindex. Which is going to happen is we're going to reread all the data, reanalyze the distributions to get the best mathematical function, and then resort the table by that particular value. And then you get performance back again. Very useful feature. We are getting started with the feature, making it better, making it more useful, making it faster to do different things. There is a load penalty because there's some mathematical calculations that need to happen. But I highly recommend you try to see. Now, normally, this feature is not very conducive for range scans for date. So if your main filter is like a date range, that might not be for you, but you should try, just to make sure that all your generic queries work better or worse with that feature. Now let's talk about migrating your existing workloads. If you don't get anything else out of here, Don't forklift your system. Because it's going to be fast to create new tables on Redshift, load the data, point your system to Redshift, and okay, I'm done. Right? You're going to spend a lot of time tuning and troubleshooting when things go wrong. Don't do that. The problem is a lot of legacy data warehouses have some patterns of usage that people have used for tens of years. And they are actually anti-patterns for Redshift. For example, I've used to load large tables with a single file, extract a single file and load to the final system. And we already talked about single file, not good for load. Or I run many updates on my data. I load my data, and then I massage, and then, okay, now it's good. Right? Instead of doing a one-step processing, that's more complex, hard to write, but you do a single step. You massage the data, and that's anti-pattern for Redshift because of updates. We're going to talk about that. Or every job clears all the data for the day before loading it. I'm not sure if I loaded yet or not, so I'm just going to clear the data. You should know if you load your data or not. You should not just clear. It's like, I'm not sure if I have breakfast or not, so I'm just going to, anyway, you get the idea. Or you count on primary keys to avoid you from duplicating your data. Again, Redshift does not enforce primary keys yet, and you should make sure you know what you load in your data. The other thing, it's a normal pattern on other legacy data warehouses, is that you have a high concurrency of load jobs. And the reason is, a single job on a regular legacy data warehouse cannot use all your hardware. So if you load one table at a time, you're never going to be done. So you have to load 10, 20, 200, 2,000 tables at a time, because then the different jobs are kind of using more of the hardware. That's the way for you to utilize the hardware you bought and you're paying for. On Redshift, it's not quite that. On Redshift, a single job can use the whole cluster, all I/O, all CPU, all memory. And it might be better to let it happen this way. We're going to talk a little bit about that in a few seconds. And the other thing, which is a pet peeve of mine, is you create a small control table to control your load process inside the target data warehouse database, where you do a single row insert, a single row update, and then a single row update again, and another single row update, and then an insert, and then another delete. And over time, those transactions are expensive in Redshift. And you get in a way of actually loading your data. We're going to talk a little bit about that as well. When you start your process of migrating to Redshift, I want you to ask two questions. First, why you do what you do? People may not know. Or it might be a limitation that doesn't exist anymore. Or it might be a limitation that you know the new system does not have. Right? You should know why you do what you do. We've always done this way. Why? I don't know. Right? You have to know. The other thing, what your customer needs. The system that was developed 10 years ago may not meet their requirements anymore. Since you're going to get a new system, why not get the fresh requirements? Understand what they need now so you can implement it. And on the process, you might even benefit from using other AWS services that can make the whole package much more attractive for your customer. So on Redshift, why those things are anti-patterns? An update on Redshift is a delete and an insert. There's no real updates. Blocks are immutable. And of course, the deletes themselves are not real deletes. We mark the row for deletion, and later on vacuum, we clear the data. So it can be expensive to update over and over again many rows, a single column of a table. Blocks are immutable. The minimal space used by a table is one block per slice per column. Blocks are 1 megabyte. You do the math. So you want to load thousands of rows at a time, not single row operations, because then you add a block every time, per slice, per column, and it becomes expensive at the end because your table grows a lot and there's not a lot of data there. Commits on Redshift are expensive because they're designed for batch processing. Every commit is about 4 gigabytes write on each node on an 8XL node. It mirrors the whole dictionary from the leader node to the compute nodes for recovery, just in case you break right after the commit. And it cluster-wide serialized. So there's no such a thing as small commits on Redshift. You want to make the most of it. Batch your work and do many steps and then a single commit. On Redshift, aggregates can be really fast, especially if the first column of the group by matches the distribution key, because then we can do a single-step aggregation. All the data is already on the same node. If that is not true, you might want to do a pre-aggregation to reduce the amount of data that goes across nodes. Or the order of your group by can change your performance. Because if the first column of the group by is not the distribution key, but the second is, you just flip them, and you can see the difference. Try me on that. Concurrency on Redshift should be low, especially for load jobs, because every job will have the opportunity to use the whole cluster, use the whole hardware you paid for. For reads, then you have heavy reads and small reads, and then small reads can play together well with other reads going at the same time. But very heavy reads, the less concurrency you do, the faster the whole thing runs. So instead of thinking about how long it takes to run one job, or thinking about how long it takes, how many jobs I can submit at the same time, think about how long it takes to run the 2,000 jobs I have to run today. And you can tune it up, the concurrency, one at a time, two at a time, until you find the ideal. Usually the writes will be good at low concurrency, and small reads can be good at high concurrency, and large queries is somewhere in between. And you can test this. If you have a dashboard that you want to connect against Redshift, make sure you have a caching layer in between to protect the cluster from repeated queries of the exact same data. That will take a long way, and you can save money by having smaller cluster with a cache on top than have to have a huge cluster so you can get the performance. And of course, think about dashboard, think of QuickSight. Who's looking at the QuickSight already? It's a great tool, and the spicy thing in the middle can be a great thing to put in front of Redshift. I highly recommend you look into that. It was made for Redshift. Now, workload management on Redshift, we call WLM, it parses only RAM to different queries. So you should configure different queues for different usages. And there's a new feature that's in right now that I'm going to talk to you about. When you create data from Redshift, sometimes you need to get not only the data, but the metadata about the data, what the name of the columns. So you run select or Java, you can get that easily from a query, no problem. On Redshift, when you extract a lot of data out, we recommend using unload, which in parallel write files directly from the compute nodes into S3. However, we don't give column names on the files yet. And that's as far as I'm going to go on that. But what people do is they run the unload, and then they run the same query again with 1 equals 0 at the end, so people can get the metadata of the columns, like names of the columns and things. The problem is very complex queries. By the time the optimizer gets to the 1 equals 0, it already created temporary tables, already loaded a bunch of data, and it kind of takes the same time as the original query took. Instead, until we fix this, you can do a select top 0, because the optimizer we know right off the bat is a fake select, and it runs much faster. We made available recently a number of open source tools for you to manage your database. I'm a 25-year DBA, and I like to have my scripts to do things on the database. And I got those scripts along with other people that helped a lot and put this together and made them available to everybody. So we have multiple sections that I highly recommend you keep your eyes on this. It keeps growing, keeps adding new things and making them better. We have admin scripts with a bunch of tuning and monitoring for the database, views to get DDLs out of table, permissions, things like that, column encodings, a tool for analyzing vacuum, a tool for unloading and copy move data from one cluster to another cluster. I highly recommend you take a look on that. The bottom 3 are Python written tools. You can get the source code, change, make it yours, make it better, give us suggestions, give us, hey, this is broken, we're going to fix it. Make contributions. We love to have your code being there too. Now, for the admin scripts, I'm going to show you a few of them so you can have an idea of how they work. So imagine you want to tune your workload. Your cluster is not quite running as fast as you want. So the first thing I look, top queries. What are the queries that are using most of my time on my cluster? Either because a single query, like the first one, takes a long time, or the second one there, where it runs too many times. It's fast on itself, but runs too many times. And then you can go and see, how can I fix those queries? Of course, on the right side, on the event column there on the right, you see there is some of them that says filter or stats. Those are performance alerts where the system is telling you what is wrong with the query. You're missing stats, or the filter is not appropriate for the sort key of the table. Another way of looking at your performance is looking at the summary of your alerts related to a particular table. So you summarize all your alerts per table and also add the number of minutes you spent scanning that table. So you have a prioritized order of which tables you can fix, and if you fix them, everybody that uses that table benefits from the performance improvement. For example, this particular flights table needs a new sort key, or maybe needs to uncompress the sort key. I don't know. We have to look specifics there. But then get to a point where to start your work. Another way of performance tuning is to making sure that not my queries are running fast, but actually I'm not waiting in queue. If I'm submitting more queries that can run at the same time, if you look on the WLM Apex hourly, it's going to give you per queue and per hour what's the pressure on the queue. My queue is 5. I have 10 people waiting in line. Maybe the queue needs to be adjusted, right? And now that we allow you to change the memory and the concurrency of the workload management on the fly without bouncing the cluster, you can change those parameters throughout the day. For example, you're going to start your load process. You give more memory to the queue number 1 there. And then when your ETL ends, you go back to 50-50, for example. It's an example, right? Now, this is all to point you to a particular location and where to look. Now, you're going to ask me, okay, how do I tune a specific query? How do I know? Explain plain is kind of fuzzy. I kind of know how to read the explain plain, but those queries are big, right? How do I know exactly what's going on? So I'm going to show you something we launched some time ago that I know many of you haven't used yet. It's the console and query detail for the console. So imagine you have a query that runs on the console that has the query and the explain plain on the bottom, but you don't know each of the steps really took longer. But then you click on the actual tab, and voila, you have a list of all the explain plain steps and how long each one took, if they are unbalanced or not balanced skewed, and you can even get details about a step. Like how many megabytes, oh, 29 gigabytes of data transmitted. That's why that step was slow. And you can figure out what's going on. It's a very good tool when you narrow down to one query, what's wrong with that query, and then you can go and fix it and understand exactly who is contributing, where you need to fix. Sometimes multiple steps look bad. Oh, distribute data across the network. That must be bad. Well, if it's 10 bytes, it's okay. If it's 10 megabytes, okay. 10 gigabytes, that is really bad. So this can tell you exactly what's going on, which step of the query took longest, and help you figure out. And even if there's alerts, they're going to show here, hey, this table is missing stats. That's your problem, right? So I highly recommend you take a look on this, and I hope you can enjoy tuning on Redshift all the performance those customers show in the beginning. Now it's my pleasure to bring Ari Miller from TripAdvisor. He's going to tell you how they created their environment to get the performance they needed from Redshift.
So I'm going to talk for about 15 minutes, and then we'll have 10 minutes at the end for questions, because I know I have some follow-up questions. This presentation is about sharing Amazon Redshift. So it's how do you maximize your particular cluster, especially with a whole bunch of different users using it. It's a variety of patterns we're using, some tools that we're in the process of open sourcing. Hopefully you guys will recognize some of these problems and be able to benefit from some of the patterns that we're using or some of the tools we've built. So a brief introduction, TripAdvisor's 375 million unique monthly visitors. We're using a fairly small cluster. It's an 8-node DS2, 8x large. Our largest table is 12 terabytes. It's got about a month of data, and everything for us is time series. So we're really not about real-time analytics. Most of our use of Redshift is about understanding user behavior, what people are looking for, and how we can better serve them. We have a big shared resource problem, which is we have about 460 engineers, data scientists, analysts, and product managers, all of whom have personal logins to Redshift. They've created more than 2,500 tables, and our experience has been that if you don't build it, be it infrastructure or whatever, they're still going to come. The company motto is speed wins. There's no tolerance for delayed analysis. If we don't make the correct path, the easiest path, they're still going to find a way to accomplish it. It will just be accomplished in a way that interferes with the other 459 users. My favorite recent example was one of our data scientists needed to bring over a 293 million row table, and we hadn't communicated as well as we should have how you would do that. And so they noticed that you could just use JDBC and do a bunch of insert statements. And it worked, but it kind of crippled some of the underlying Redshift views for query monitoring, because you now have 293 million rows in those underlying tables for each individual insert. So those are the kind of things that happen unless you establish the patterns and the tools that users need. They will find a way to do it anyway. So our solutions really break down into 4 points. Reduce contention. So where you're doing something expensive that you control, find a way to do it on a custom cluster that's really effective for what you're trying to accomplish. And I'll talk specifically about the types of custom clusters we use for different types of tasks. Add infrastructure and automation. Add a lot of monitoring, tables, performance, and usage. And where you can, if you know everyone's trying to accomplish some similar goals, do as much of that as you can yourself so that they can then benefit and just query instead of doing the ETLs, and have 5 people doing the same ETL. So for custom computation clusters, your goal there is to stay out of the way. And our favorite type of custom computation cluster from a performance and cost perspective is what we call a Mighty Mouse cluster. And that's a specialized ephemeral cluster. The Mighty Mouse one in particular is 32 DC1 large nodes. So that's great bang for the buck in terms of a lot of computation cases. It's $8 an hour for the whole cluster for all 32 nodes. For a 4-hour job on 8 D1Ss, you can end up doing it in 40 minutes on a Mighty Mouse cluster. So you can get some real performance wins. The D2s for us, we've seen 50 to 200% performance improvements compared to the D1s. Thus Eric's advice to, if you're still on the D1s, get off. So much smaller wins versus the D2s. But if you look at performance per cost, you can still see 3x better performance per cost for a lot of use cases compared to sort of the bigger nodes. So we had 7 of these 32 node clusters running last week doing some custom computation, and we ended up saving, it's about 3 times cheaper than it would have been had we done the same computation on the D2s. Some of the wins you're getting are that you can customize the configuration of these ephemeral clusters. So as Eric was saying, Redshift is really good at parallelizing and operating a single query at a time and spreading the workload over nodes. So we'll a lot of times run with 2 slots only to maximize the amount of memory available to each query. And that's been very effective on us. You're just relying on the underlying technology to parallelize across the nodes. You do have to be careful, right? If you're making any mistakes in your query that are causing nodes to need to talk to one another more than they have to, that blows up when you're dealing with 32 nodes at a time. So you have to experiment, make sure you're doing things in an optimized way. But it actually is kind of a good way, canary in a coal mine style, to really know that you're not doing something effective with a query. Because while you might get away with it with 8 nodes, if there's bad distribution keys or too much node communication, it really blows up once you start talking about 32 nodes at a time. The primary limitation we found with these custom computation clusters is the size of the copy. So with 32 of these nodes, you have 5 terabytes of storage. But if you're trying to bring in, for us, anything more than 300 gigabytes compressed, you end up in the process of bringing it in using all the available space on the cluster, and your load will fail. So it's not an awful limitation, but you got to keep that in mind. Like, just because you have 5 terabytes usable on a cluster like this doesn't mean you can bring in 5 terabytes of data compressed all at once. The additional pieces of infrastructure, and as I said, we're in the process of open sourcing some of these. If you're going to use custom computation clusters, you don't want to rebuild your cluster every time. You want tools that let you say, hey, OK, I need this schema for my main cluster on this ephemeral cluster. So we have some of those tools. Sync Redshift objects is basically a way to bring over entire schemas to an ephemeral cluster from your main cluster. We have specific unload and copy for transferring the data back and forth. But it sounds like some of the tools that Eric's already open sourced might be more effective than that. One key thing to keep in mind is use a manifest file wherever possible. With analytics, it's much better to fail than it is to lie. And a really easy way to lie is to get into trouble with eventual consistency in the standard region and only have some of your files that got unloaded available at the time you do the copy. So I heavily recommend whenever you're doing an unload or whenever you're doing a copy, you take advantage of the manifest file option. Don't find out later that you've come to the wrong business decision because you only had 80% of your data at the time you copied back in. The next bit is infrastructure and automation. And the easiest path there is to start with your engineers. So what can you add that lets engineers take advantage of things you've built for yourself already? And one of the things that we're using is something that LinkedIn open source called Azkaban. And that's a batch workflow in UI and scheduler. And it's really very easy for people to adopt. It's nice. You can basically divide your logic for bringing data over or running SQL into a series of jobs. And it'll create visual dependencies for you. You can parameterize running your jobs. You can parallelize running them. You can visually see when things are happening. It gives you a list of how long things take. So you get a whole bunch of things baked in. And it's a very easy adoption for engineers. So these jobs get run, and Azkaban's calling the data transfer infrastructure that we've already built. So that's been very effective for us in terms of as a scheduler and understanding dependencies and making sure things happen in the right order. And to Eric's point, we actually have a normal Postgres admin database that's tracking what runs when. We're not trying to have a small control table that we're doing lots of individual writes to in sort of a transactional way that's living on Redshift. So that's another pattern that you might want to make sure to copy. Once you've handled the engineer problem and you've given them a pathway for writing custom flows, and we're at about 70 individual flows that different engineering teams have created at this point with their own independent schedules, you want to go for solutions for your data analysts, your data scientists. Give them a way to have a point-and-click UI for scheduling. So custom UI for non-engineers, something that allows you to import from File or Hive. And as I said, we're in the process of trying to open source these solutions. What we do in these cases is we auto-analyze the source data either from File or Hive. We suggest a table DDL, sort, distribution, and compression. And we can schedule automated imports and automated runs of particular SQL. It was probably a mistake to have automatically suggested compression. We probably would have been better off bringing in a subset of the data and relying on Redshift to suggest the compression, or just not trying for that at all and relying on automated Redshift. It depends whether, as Eric said, if you're doing something over and over again, you're better off eventually coming up with the compression through an analyze. If you're just doing a one-off, much better off just not to specify compression and let Redshift do it. The next thing we added was monitoring. And the key thing to keep in mind here is you've got compatibility with Postgres. So you can throw up simple monitoring that's emailing alerts out with a simple query statement and then emailing the results of that query, which is what we're doing at the bottom. So we have long-running query alerts. Every account that gets created is mapped to an email address, so we know who to tell if a query's gone off the rails of these different users. We have daily and peak usage reports by user and type of activity, daily table size, space taken up by deleted rows by table. We tend to use deep copy instead of vacuum because by the time we see that a table is a problem, we're well over the 20% where you're going to be feasible to vacuum. And as I said, the initial monitoring cost for this type of solution can be really, really cheap. All you have to do is write a query like that, pSQL, quiet, HTML output. You go from a file, do an output, and then email it out to whoever needs to be notified. So it's just a very simple way of setting up alerts, seeing if they have value. We've actually found a slightly better pattern is to insert the results of the query into a date partition table. So you have a record of what things were going on at what time. And you can build dashboards on top of it. Then you select, and then you email. So slightly more complicated, but it gives you a historical record. For things that prove themselves out on the monitoring side, you can then do things like build Tableau dashboards on top of your monitoring. So this is, different size is for different users is how much of the cluster resources a given user is taking up. So we can start knowing who to communicate with if someone's sort of overly aggressively using different cluster resources. The next thing I wanted to talk about from an engineering side is a shared development cluster. So you obviously don't want to be doing most of your development on your main clusters if you're testing out. We had a good example for us. We had people testing out new uses of the list ag query. And we found you can take up 10% of the usable space on a fairly large cluster in about 30 minutes if you use the list ag query wrong. So you want as much of that to happen not on your main cluster. So what we found can be very effective as a shared development cluster. And we use something we call Khaleesi syntax after the engineer who invented it, which is a very simple way of marking up the schemas in your query. So what this lets you do is, if let's say a given flow, a given sort of unit of work might operate on a particular schema. To say we're looking at something like hotel bookings. What you do is you mark it up. So everywhere you reference that schema is noted like this. So it's completely legitimate SQL, can run as is, but it's marked up in a way that lets a tool do substitutions. So when people are operating on that flow, trying to engineer it and make it better on the shared development cluster, you can automatically create copies of the schema that this runs against for their own personal users. So if both Jeff Bezos and Werner Vogels wants to develop on the Sherpa flow, you basically can just have some tools that go and create them their own version of the schema and run against that schema and use the same precursors. So rather than having the overhead of spinning up an individual cluster per user, you can instead all operate on the same shared development environment. And as I said, we're working on open sourcing this, so it'll be sort of available if you guys want to see exactly what we did, but feel free to reach out as well. So here's a little bit of example code for what we do to do that. You can see it's not particularly complicated. We're creating a schema. We have a target schema, and then the schema for the individual user. We just go through the tables. We load the information, and we substitute basically for the schema so that we can recreate the entire schema and clone it over to another schema that's personalized for the developer to operate on. The next trick I wanted to talk about is view performance. This is actually less relevant because of the recent improvements that they've made in view performance. But you can also mark up views such that if a user is using your tools and you note that they're using a subsection of data that only comes from one table. As I said, we're using the time series pattern. So we tend to divide our tables up by months. So we can drop old months without having to deal with vacuum costs. And you can find that pattern in the Redshift documentation. So the syntax is completely legitimate SQL against a view. You can have it autocomplete if you're developing your SQL in an IDE. But your underlying framework can substitute in and run against an individual table instead of using the view to get performance optimizations that way. As I said, a lot less relevant now that the view performance is around as good for union all type views. But it used to be a very large win to avoid doing running queries against union all views. Final thing I wanted to talk about is queue management. So the idea there is keep it simple because the memory is reserved. Though you no longer need to keep it as simple because you can now dynamically move queues around without actually needing to reboot your cluster. So we have 4 queues, for example, mission critical queries that might run a while, a queue for basically shared computation, the DBA queue, a quick queue which we use for Tableau. So if you need to run quick queries to find very quick answers, or for Tableau dashboards where you need immediate responses, but don't use a lot of computational resources. And then a default queue that everyone fell in. We have a default timeout, so when some user does a Cartesian product on a 12 billion row table, you don't end up bringing the whole cluster down for 3 hours. It's only sort of slow for 30 minutes. And so that's been pretty helpful to have default timeouts on the particular queues. And then groups allow you to dynamically switch queues for particular users. So you can associate a group with a queue. And you can dynamically move users from group to group. So for environments like Tableau where you can't set your query group, you can actually just have UIs that let a Tableau user move between groups depending on whether it's loading a large extract or just servicing the needs of a dashboard. So we found that to be pretty effective where users can't set their own query groups as a way to dynamically adjust which queues users fall in. So in wrap up, Amazon Redshift has transformed analytics at TripAdvisor. We get thousands of queries a day, hundreds of users, and all on not that large a cluster. So you can really optimize your use of a cluster if you really spend the time to optimize it in these ways. We generally use Tableau dashboards built directly on Amazon Redshift, and it allows for iterative real-time exploration, which is hundreds of times faster than poking around in Hive or a variety of other options. And we have open LDAP access for any employee. We had to do a little bit of custom work to just sort of automatically create instead of manually create accounts, but the LDAP access and ability to plug into LDAP repositories is, I think, coming at some point. And we're going to be open sourcing these solutions. We're currently targeting February of 2016, but if there's anything you're particularly interested in early, feel free to reach out and contact me. We're just trying to sort of divorce some of our custom stuff from some of the more generically usable aspects of the tools we've built. And some of the patterns are usable now. And when we do open source it, you'll be able to find the link at http://engineering.tripadvisor.com. Thank you very much.
So another example of a customer that started with Redshift and created their own environment around it. There's those other sessions where other customers are discussing their use of Redshift. Some of them already happened, and you can go on the archives on the video or audio or the share of the slides. But the ones that are still going to happen, I highly recommend you take a look and see what you can learn from Redshift. Now we're going to take a few questions